Okay, so yeah, let's get started. Today, the focus is going to be on floating point numbers. And again, we'll start with some announcements. So we just had a question about programming assignment 1, when to expect the grades to be released. So overall, there should be no surprises on what you're going to get programming assignment 1. The TAs, Abhinav and Niraj, are handling the grading of PA1. It's mostly automated, so we should be able to get that out onto the grade book this week. But like I said, there shouldn't be major surprises. The grade that you see from running the autograder and tallying up the autograder grades that gives you, that should be the same grade that you'll be receiving from the TAs. And if there are issues or questions about the grading of programming assignment 1, direct those questions to Abhinav and Niraj. So let's do a look ahead of where we're heading in class. So today we're going to talk about finally floating point numbers. There's a new quiz out, quiz number 5. Okay, so there's actually 2 different quizzes out. Quiz 4, I released yesterday. It is a survey intended to help you reflect on programming assignment 1. I want you to think about what you learned in PA1, how long it took you, and what were the most useful resources for solving programming assignment 1. There is also a new weekly short quiz out, quiz 5, that is due on Monday, February 22nd at midnight, as usual, where it's going to quiz you about bits, bytes, bitwise operations, signed and unsigned integers. So those 2 quizzes are both, one is survey 4, that's ungraded, it's anonymous. You can find all of that within the quizzes section of Canvas. All right, and I just want to make a special point about quiz 5. So quiz 5, I designed it so that you can solve it using experiments by running the code on iLab. But the point is, I want you to know what's going on when you run the code. I want you to think about what's happening in terms of the integer representation in bits and bytes, and how you're getting the answer that you're getting. Okay, so let me see if there's any questions about quizzes so far. Okay, so there's some confusion on where is survey/quiz number 4. You should be able to find it on modules, but I'll double check after lecture after recording the lecture to see if it's all showing up correctly. All right, great. And looking ahead in terms of our lecture plans. So today and possibly overflowing into Tuesday, we'll talk about the representation of floating point numbers. And then after that, we're ready to move on into the next major chapter of this course, which is talking about assembly language programming. How exactly does software interface with the hardware? And next Thursday, we'll be releasing the 3rd programming assignment. This is a relatively shorter and quicker programming assignment, which is going to be about data representations. So bits, bytes, floating point numbers. All right, so let me just pause here and take any questions about the overall course plan. Okay, so today is all going to be about fractions and floating points. So first we'll do a quick review of fraction numbers that we talked about on Tuesday and how we represent those as fixed point numbers. That motivates using numbers where we can move the decimal point around, so hence the term floating point. And there's a little bit more involved to understanding how floating points work. So we'll work through each of the different cases and how to interpret floating point numbers. So first, let's just do a quick review of Tuesday's class, where we talk about the binary representation using fixed point numbers for fractions. So the idea here is very similar to representing integers. Right? So we have zeros and ones. We continue to use 2's complement notation for positive and negative numbers. The only difference here is we can introduce this idea of a decimal point. In this case, this point is fixed. So we say in this format, for example, we have m bits to the left of the decimal point and n bits to the right of the decimal point. Left of the decimal point are whole numbers. And to the right of the decimal point, we have fractions. So numbers smaller than 1. And the positions of each of these bits, they correspond to powers of 2. So to the right of the decimal point, we have fractional powers of 2. So 1/2, 1/4, 1/8, and so forth. And this again is just recap. So this is how we would represent that in binary numbers. So each of the digits, each of the bits here correspond to some weight in base 10 numbers. And to convert from decimal numbers, base 10 representation to base 2 representation, you would work through each of the digits one by one, and you get a representation like this. Okay. So this is basically an extension of integer representations. We can add a decimal point to turn it into a fixed point binary number. So we also really briefly talked about what are the limitations of this representation. So one is that you can only represent numbers precisely that are the form where they can evenly be divided by powers of 2. So the number has to be in the form of x over some power of 2. And the fixed point representation, you can't use it to represent really large magnitude numbers. So any number that has a lot of dynamic range, or very small numbers. So numbers that have really high precision. Neither of these types of numbers you can represent using fixed point notation. Okay, so just want to take questions real quick about integers, fixed point, before we head into floating point numbers.
Just out of curiosity,
Sure.
how do computer systems, when representing fractions, how do they represent, let's just say, an example of a mixed fraction, so a whole number preceding a fractional number?
That's a good question. So mixed fractions, right? And so here we actually already all are working with the mixed fractions. So for example, you talked about a whole number followed by some fraction smaller than 1. So this is a mixed fraction here, 9.5. 9.5, you can break into the whole number portion, 9, and 0.5, which is the fractional portion. And you would represent them each separately. So 9 in binary representation is 1, 0, 0, 1. It's 8 plus 1. So that goes to the left of the decimal point. And 0.5 is the fractional portion here. And it is just 1/2. So it's a single 1 in the 1/2 place.
Okay, and I don't know if, I think this question was asked before, but I don't know if it was answered, but is the decimal point in these examples, is that just for readability, or is that actually stored in the system?
Okay, yeah, that's a very good question. So where does this decimal point actually show up, right? So I want to emphasize that really this whole little subchapter that we talked about here, this is just to get us warmed up for thinking about floating point numbers. So what you could do is, if you wanted to have some design of representing fractional numbers in your own program, you could set up a system where you have an integer and then divide that by some power of 2. And you can use that to represent fixed point numbers. But natively, in either the C programming language or in most common types of hardware, computer hardware, there is no such thing as fixed point representation. This is just for us to set up to motivate the actual representation that we do use, which is floating point numbers. So I'm seeing a question from Michael, which is, what does the little 2 at the end of representation of 9.5 mean? So this little 2 subscript here is just my way, a common way, one of the ways that we use to emphasize that this number you're looking at here, this is a base 2 number. And Xiaowei is asking, technically, we can represent really large magnitude numbers and really large, small magnitude numbers, so long as we have enough bits. Yeah, so you could use a lot of digits to get the range that you need, but that ends up being not as flexible as a representation. It's one of the limitations of fixed point numbers. In fact, it essentially makes it so that you have to trade off between representing either really big numbers or either really high precision numbers. Okay, so let's move on now toward floating point numbers. All right, so again, we'll go through an overview of what floating point numbers are. And then the detail of this is we need to work through different cases of interpreting floating point numbers. So what are floating point numbers? Everyone can recall that one of the most common ways we represent numbers in science, for numbers that have really big range, for example, or numbers that are very precise, is very oftentimes we'll represent it in scientific notation. So for example, we know about Avogadro's number, which describes how many particles that there is in the mole, right? So this is a review from chemistry or from physics, where oftentimes we want to have some number that describes a really large collection of particles, atoms, molecules, and so forth. And it would be really cumbersome to write this number out as a number of 23 digits. And so what we do instead is we take the significant digits, we write out a few of those, and then we say that this is a number times 10 to the power of something. So here, Avogadro's number is 6 something times 10 to the power of 23, right? And so this shows the essence of scientific notation, which is we take any number that we want to represent, we break it down into different components. So first we say if the number is a positive or negative number via the sign. And then we describe the significant digits of the number. Here, this terminology for this is called mantissa or significand, right? So for Avogadro's number, the mantissa is 6.02 something. And then finally, we describe what is its exponent. So we describe this number is actually times 10 to the power of 23rd. And so for Avogadro's number, the exponent is 23. Okay, so in the chat box, somebody says, okay, well, yeah, it's Avogadro's number, not Avocado's number. Right, so everybody's familiar with scientific notation. And so essentially, we want to be able to use scientific notation in our computers. And so computer scientists and electrical engineers came up with different standards to describe floating point numbers. And so there's a little history here I want to talk about. So before 1985, there were many computer companies, each of them would implement different floating point systems. So they each would come up with a different system for representing scientific notation. And so a little story here is shortly after I graduated from college, I worked at a company at Boeing, which is an aircraft company. They did a lot of scientific simulations for things like airplane, airflow, and so forth. And so they were one of the earliest users of supercomputers to do aerodynamics modeling. And so they were some of the earliest users of really specialized hardware built by companies like Cray supercomputers. And these types of machines, they were developed not before 1985, right? They were already doing computer-aided design of aircraft before 1985. And so they were using computers that had a wide variety of different ways of encoding floating point numbers. And because only those machines supported those specific types of floating point encodings, the Boeing company, the IT workers there, were forced into a situation where they actually had to keep some of those really old machines alive and running to run legacy software, because the software relied on those really esoteric ways of encoding floating point numbers. Right, so this was an unsustainable situation that every company was developing its own type of floating point encoding. So in 1985, the IEEE, which is a industry organization for electronics engineering, they came up with their standard number 754, which describes the standard way of encoding scientific notation numbers, of floating point numbers in computers all around the world today. Right? So they designed the standard to have really nice properties, to do very precise mathematics, and to be able to handle a wide range of numbers. And you can find and use floating point numbers in almost every single computer today, except maybe for some of the tiniest, lowest power microcontrollers. Right? So even if you pick up an Arduino, which is a kind of really tiny computer that you can use for experimenting with computers, you'll find that that Arduino itself already supports something like floating point computation. And in terms of more recent history, we're starting to realize that actually there's a lot of situations where even the floating point standard that was built in 1985, it's starting to not really match with some of the needs that we have right now. So those needs could be, for example, we want to be able to do fairly approximate calculations, right? So in things like machine learning and neural networks, you don't actually need the really precise calculations that floating point number offers. In fact, people have looked into building specialized hardware where multiplication is relatively imprecise. It only uses maybe like 4 or 5 bits to do multiplication. And they're showing that they can use this type of hardware to do neural network pattern recognition by trading off the precision of the floating point number in favor of more efficient computation. Okay, so this is just kind of a big picture view of where we got to the standard and where it's heading into the future. All right, so I'll take some real quick questions here before we dive into the mechanics of floating point numbers. So there are 2 major encodings standards for floating point numbers. And you probably know these 2 different encodings as floats and doubles. So this is a data type that you have access to in both Java and also C. And what they describe is 2 different levels of precision for floating point. So single precision is what we call float data type. It has 32 bits, and those 32 bits are broken down into different fields that are listed here. And we'll talk about how to interpret each of these fields in class today. The other major encoding is double precision. So here, double precision, it uses 8 bytes. It's overall going to be 64 bits long. And this is encoded in a very similar way to single precision, but the double precision offers greater precision. It offers more precise calculation. All right, so let's go into some of the differences between these two encodings. So like I mentioned, the float data type has 32 bits. The double data type uses 64 bits. For both of them, you would look at the number, the binary string that encodes the floating point number. And both of them have 3 different fields. So the S field, the exp field, and the frac field. Okay. So in both of these, you dedicate a single bit to indicate the sign, which is if it's a positive number or a negative number. If it's a negative number, you put a 1 in the S field. If it's a positive number, you put 0 in the S field. And then you have a few more bits dedicated to encoding the exponent, which we call the exponent field. And in the case of floating point numbers, that's going to be 8 bits. And for double precision numbers, that's 11 bits. Okay. And finally, almost all of the bits are dedicated to encoding the fraction. So what we call the frac field. And essentially, when we go from floating point, single precision floating point numbers to double precision floating point numbers, we dedicate most of the bits that you're adding to that format. Most of it goes to the fraction field. And this is to enable you to encode really precise numbers. Okay. And this is just a little note. Within C, you can access these data types. You can print them out using these format specifiers. Okay, so any questions here? Let me also take a look at the chat box. So Yuchen is asking what are exponent again? What is EXP? So the EXP field is going to be used in a tricky way to encode what is the exponent. So for example, here we'll want to encode Avogadro's number. We're gonna encode the exponent as which is 23. And we'll talk about the encoding how we encode 23 into this field here. Okay, so Swapnil is asking, so there's additional questions about the exponent. So one is, what if the exponent is negative? So we'll also talk about that. There's a special encoding for encoding negative exponents. And Swapnil is asking, what if the isn't the exponent supposed to be a power of 2? So right, so this is just an example. This is a number that we're representing in base 10, but in floating point numbers, we'll encode the exponent as a power 2. The exponent is going to represent 2 to the power of something. Okay, so what we're going to do now is we are going to head into talking about the different cases that we need to consider when we use floating point numbers. And the key thing here is we want to use this encoding, we want to use this floating point standard to encode an extremely wide range of numbers. So we want to have some way to encode sensibly negative infinity all the way to positive infinity. And we want to have a really wide range of encodings, of numbers that we can encode. And at the same time, we want to have really high precision in numbers that are more commonly encountered day to day. So we want to have a way to make it so that you can encode really high magnitude numbers at relatively poor precision, but also at the same time, you want to encode really small magnitude numbers at extremely high precision. So this is the nice part about floating point numbers. You have this ability to trade off range and precision. And it does this by having different classes, different cases to encode different types of numbers. So there's a special encoding for infinities. There is a common type of encoding called normalized encoding, which covers most of the number line. And finally, when you get really close to 0 for extremely precise and really small magnitude numbers, so for example, we zoom in down on the number line here, you'll see that around 0, very close to 0, we have a class of numbers called denormalized numbers, which the whole point is to be able to encode these really precise numbers in a specific way. Okay, so quick questions on this slide here. So Yushen is asking, I think Yushen's asking about kind of exceptional cases. So we'll talk to you about that. Purva is asking about, can we encode infinities in this format? So yes, so this number line, this format, we're able to have a specific string of bits that represents either negative infinity or positive infinity. Okay. So thing I want to emphasize here, right? So this is not exactly the real number line. There are many numbers, real numbers that exist that do not have an encoding in floating point representation. So for example, out far into the, when the range is really big, the precision is not very high. So there are many numbers that there is no exact mapping into the floating point format. The key thing here is floats do not exactly translate to representing real numbers. The IEEE 754 floating point number line is not the real number line. Okay, so we'll come to appreciate that as we get through this lecture today. So what we have to do now is we continue, we were trying to get to the point where we talk about the different cases for interpreting numbers. We need to understand how to interpret normalized numbers and also denormalized numbers. And in both cases, essentially what we're doing is we are trying to find a mapping for how to interpret the EXP field and also the frac field. All right, so these fields, they encode the information, but it's not exactly one-to-one. There's a little bit of a tricky mapping to get the most use out of it. So in all cases, for all floating point numbers, the number that we're representing, the real number that we're representing, can be described via this equation. So it's -1 to the power of s times m times 2 to the power of e. So this is the number, the real number that we're encoding. So for example, if s is 1, then this becomes a negative number. If s is 0, then this is a positive number. M encodes the significant bits of our number. So for example, for Avogadro's number, M is 6.022 something. And 2 to the power of E, this encodes the how many bits, how many digits that we're gonna shift the floating point. So this describes whether we're talking about a number with big magnitude or really high precision. All right, and so E is encoded via the EXP field and M is encoded via the frac field, but the mapping is not exactly straightforward. And to understand how that mapping happens, we gotta consider two cases, normalized numbers and denormalized numbers. Okay, so Devim is asking, what is M again? So M is the mantissa. So for Avogadro's number, for example, in base 10 notation, M would be 6.022. But of course, you have to have a binary number representation of M. Okay, so we've motivated that we've got to consider two different cases, normalized numbers and denormalized numbers. And back from our number line again, we kind of see that normalized numbers are quote unquote, they're normal numbers. They're numbers that span a great majority of the number line, while denormalized numbers are special, relatively special cases that are very close to zero. So first we'll cover normalized numbers. Right, so this is going to be the more common kind of number, a floating point number that you have to understand. And so when we consider normalized numbers, again, we'll consider each of the fields separately. So in this case, right, so there's the EXP field that we got to consider, and there's also the frac field. And we need to understand how those translate to the actual real number that we want to encode. So first we'll focus on the EXP field, and then we'll talk about the frac field. Okay, so the EXP field for normalized numbers, the number is, the floating point number belongs to normalized numbers so long as the EXP field is between 0 and the maximum possible number. Right, so what does this mean? So just take as an example, for floating point numbers, the EXP field has 8 bits in it. And so the EXP field can range from 1 inclusive up to 126 inclusive. All right, so EXP is used to encode the exponent, but here we encode it as a k-bit signed integer. And so long as that EXP field belongs between these ranges of numbers, this floating point number is considered normalized. All right. And earlier, someone asked, but wait, what if we need to encode negative exponents? Right, so the negative exponent would be something like, what if we have to represent something like 1/2, 0.5 in this number? 0.5 would have a negative exponent because the number is a fraction of 1. And so to be able to encode negative exponents, we introduce a number called a bias. And the bias has the effect of shifting the whole exponent up and down relative to what the number the EXP is representing. Okay, so in all cases, this bias, this number that we shift the exponent around by, is this number here, right? Where K is how many bits are involved in the exponent. And so for example, for floating point, single precision floating point, the bias is 127. And double precision floating point, that bias is going to be 123. So this means that using this encoding, we can encode numbers with a range of different exponents, right? So for really precise numbers with great precision, the smallest exponent that you can encode is -126 for floating point numbers, single precision floating point. And it is -1022 for double precision, right? So it's helpful maybe that we skip ahead to work through an example of this. But before I kind of switch pages, I'll let people ask questions about this slide. maybe like motivational questions like why are we doing this, or what is the terminology that we're using on this slide. Okay, so Xiaowei is asking why are we stipulating, why are we requiring that the EXP field is greater than 0 and not greater or equal than 0? So why can't EXP be 0? So this is the reason that we're stipulating that that has to be not 0 is because we're talking about normalized numbers. And if the EXP field is actually 0, then that's the next case that we'll be talking about much later, which is denormalized numbers. Bohan is asking a question about EXP field size. So instead of asking like exactly what the numbers are, the ranges are summarized at this table here. And bias is not a range. So bias is a very specific number that depends on the number of bits in encoding the EXP field. Okay, so I think for the rest of the questions, it's more helpful now for us to kind of skip ahead a few slides to work through a concrete example. So here is our example here. We want to convert a number, for example, 12.375. This is a base 10 number. And we want to convert this to a single precision floating point number. So first of all, we have to take care of the sign. This is a positive number. And so the sign, the S bit, is just going to be 0. Put that as 0 and we set that aside. Next, we have to take this 12.375 number and we have to write down the binary encoding for it. For that, it's going to be this binary string here, 1100.011. And this is a base 2 number. The way we get that number is 12 is 8 plus 4. So that leads to the 1100. And then 0.375 is 0.25 plus 1.125. So 12.375 equals 8 plus 4 plus 0.25 plus 0.125. And these are all powers of 2. And so we can convert 12.375 into a binary representation by putting 1s in each of the digits that represent those numbers. And so this is how we get to the binary representation here. Next, in step number 4 here, the next step here is to look at this binary representation and we will move the decimal point so that we write it down in scientific notation. So in scientific notation, we make sure that there is exactly one digit to the left of the floating point, the decimal point. And we multiply the whole number by a power of 2 to move that decimal point, right? So here, we need to move that decimal point 3 places to the left to put the decimal point where we want. And to make the number equal, we multiply that whole number by 8, which is 2 to the power of 3. So now we've represented this number as a mantissa times 2 to the power of 3, 2 to the power of an exponent. And so how this connects to what we were talking about here is we were trying to talk about how do you encode the exponent in the EXP field. And so here, that corresponds to how do we encode 3 in the EXP field. And so what we wanted to do is the EXP field needs to encode both positive exponents and negative exponents. And so we shift the whole number by a bias. And so for floating point numbers that bias, single precision floating point numbers, that bias is 127. And so we take 3 plus 127. And this is what we need to put in the EXP field, which is 130. And so the EXP field is going to record these 8 binary digits, which represent 130. So Michael is asking a question here. For all float, the bias is a constant, is it? So for the value of what the bias is depends on if you're working with a single precision floating point number or a double precision floating point numbers. So for single precision, bias is 127. And for double precision, bias is 1023. So any questions up to this point? Here we're focusing on the exponent and the EXP field.
I'm kind of, first of all, the subscript 2 just denotes that it's a binary number, right?
That's right. So everywhere where I have a subscript of 2, this is just to emphasize that this number to the left here, that's a binary number.
Yeah. The things I don't get is why did we have to move the exponent to the all the way like 3 places to the left to make it to 12.375?
So the question is, why do we need to move the floating point? Why does the decimal point float, in other words? It moves around because we need to establish where that decimal point is. And so by convention, we take all the numbers that we want to represent and we write it down in this form. We write it down so that there is exactly 1 digit to the left of the floating point, and we multiply it by some power of 2 to make it the same number. So maybe I can go back to our Avogadro's number example to motivate that, right? So here's Avogadro's number. And this number is 6.02 times 10 to the 23. Well, why do we represent it that way, right? We could also just say that this is, we could also say this number is 60.2214 times 10 to the power of 22. That's the same number. Or we could say that this is 602.214 times 10 to the 21st. Or we could keep the decimal point on the other side. So we could say it's 0.602214 times 10 to the power of 24. These are all the same number. But by convention in scientific notation, we make it so that there is exactly one digit to the left of the decimal point, so that we know exactly what to put in the exponent field. This becomes a standard way of writing down this number. And so here in this case, it's the same idea. We took our binary number representation here and we wrote it down so that the decimal point is exactly where we want it to be.
Oh, so that's like scientific notation. And
Right.
does the computer store it in scientific notation when it does all this to encode a floating point number?
So your question is a little bit like a tautology. So this is the way, right? So this floating point notation is the way that scientific notation works in the computer.
Right.
The very way that floating point numbers represent real numbers is via this kind of scientific notation, via this convention.
Okay. So, I mean, I feel like this might seem like kind of I guess like not very important question, but with the binary number we got there, can you go through like how that number relates to what we broke down earlier? Like how did that turn into 1100.011?
Sure. So to do this conversion, right? So this is converting from a number in base 10 notation, turning it into a binary representation. And the steps I did to do that conversion is we have our base 10 number, and we would break it down into what are the digits in a binary number, and whether or not that digit is a 0 or a 1. And so 12.375, I can write it down so that it's 8 plus 4 plus 0 plus 0 plus another 0 plus a quarter and plus an eighth. So why am I doing this, right? So I'm writing it down in this equivalent form such that every number that I add is a power of 2. And they would have been powers of 2 in sequence. So to the left of, for the numbers greater than 0, we have 1, 2, 4, and 8. And for numbers less than 1, we have 1/2, 1/4, and 1/8. And so if the number exists, right? So if we do add 8 to this number, I write down 1. If we add 4 to this number, I write down 1 in the binary notation. Here there is no 2, so no number in the 2's digit, and so we write down 0 in that position, and so forth. That's how we went from a decimal representation of this number 12.375 to a binary representation of that number.
Also, I realized the decimal parts, they add up to 150 and not 375. It was the other thing that, like, it's 0.375 in the original number, but 0.25 and 0.125 add up to 150, right?
No, they add up to 0.375. So you got to make sure that your digits
I just
are lined
realized.
up.
I just realized what I did wrong. Yeah. Okay. Yeah.
Just make sure that your digits are lined up.
So the 8 is in is like actually in the.
So we have a visual for that, right? So the visual for that was over here. All right, so this is the same way that we converted numbers to binary representation. This is showing what the number in each position represents and
yeah.
how to encode that as a binary number. Okay, so what we've covered so far is how we use, why we have to move the floating point to get to a scientific notation. And then we talk about how we want to encode the exponent in the EXP field. And because we want to encode both positive and negative exponents, we use this bias so that we can encode the whole range of exponents that we want to encode. And so via this mechanism, we can encode exponents for a range of both positive and negative exponents, like so. The next part is we have to encode the mantissa. So these are the significant digits of the number. And here we have an interesting little, another kind of trick, another kind of non-intuitive mapping, where we make it so that the single one is implied. All right, so remember our number that we're trying to encode. Is this number here. And to encode M, we make it so that the single one is implied and we record the rest of the fraction. So let's look at that in action. In this number that we're trying to encode here, we've turned it into a binary representation. It's 1.100011. And in this encoding, we make it so that the leading one is implied and we record the rest of the fraction. So for the fraction, we only write down 10011. We truncate, we cut off the leading one. Okay, so to sum it all up, in the normalized encoding, 12.375 would have a single 0 in the S digit, in the S bit location. We would record these 8 bits, 10000010 in the EXP field. And for the fraction field, for the frac field, we encode this number here. And so that's how you would encode the 12.375 real number as a floating point number. So any questions about the normalized case?
Professor, I have a question.
Sure.
Well, how do you use like this information that we have calculated to get the real value? You know, it seems like we have gotten all the information needed. I remember earlier we had an equation that does this for us. It's like -1 to the power of s times m times 2 to the power of e.
Yeah, so this here.
So yeah.
So what I've shown you in the example is going from the value, the real number. So in this case, in that example case, how would you encode 12.375, which is a real number, and how to encode that as bits in a floating point number. So that's working from a real number to the floating point representation. And of course, there's also the other way around, which is going from the floating point number, just a bunch of bits, and turning that backward and figuring out what the value that represents is.
Okay. Okay,
so it's the same idea. It's the same idea, but you just work backward.
Okay.
The way you would work backward is you look at each of the bits in your number and you figure out what that encoding what that represents in each of the fields, and how that corresponds to M and E. Same idea.
Okay, I see. Thank you.
So any questions up to this point? We've been focusing on the normalized case of numbers before we head into denormalized numbers.
Professor, I have a question.
Sure.
Can you go back to the example slide? I'm wondering for the EXP one, the EXP equation, that how's like 130 goes to the binary expression.
Sure. So 130. Does anybody want to give a take a shot at how 130 that's encoded as a unsigned binary number? Bernice is saying it's 128 plus 2.
Oh.
And 128 is actually 2 to the power of 7 plus 2 to the power of 1. And so this encoding as a binary number would be a binary number where there's a 1 in the 7th digit, a bunch of zeros for all the digits that do not have a 1, another 1 for the 2's digit, and then 0 for the 1's digit.
Oh, okay, makes sense. Thank you.
Good question. Okay, so that is all there is to most of normalized floating point numbers. So now you have everything you need to interpret floating point numbers for the almost the entirety of the number line. There's a more tricky case, a slightly different case for parts of the number line that's really close to 0. And for these, the floating point standard has a class of numbers called denormalized numbers. So we'll consider that next. So in denormalized numbers, for denormalized numbers, the exponent field, the EXP field, will be 0. So because this is 0, the case here is no longer that this is a normalized number. And so the rules are slightly different. The rules here are that the exponent is going to be a slightly different formula. It's going to be just 1 minus the bias. And bias is really the same number as before. So just like before, bias is 127 for single precision, and it is 1023 for double precision. And after using that as the bias, the exponent for all denormalized numbers is going to be a really negative exponent. So it's going to be a negative exponent, and it's going to be a very large magnitude negative exponent. And this corresponds to the fact that we're using denormalized numbers to represent really precise numbers that are really close to 0. Andrew is asking, isn't this just the same as having EXP equals 0? So we have, this is exactly, Andrew is asking, isn't this just exactly the same case as encoding EXP equals 1? Not quite, right? So they've made it so that the rules are slightly different, and it makes it so that you have this additional capacity close to 0. Right? So not only is the rules for EXP slightly different, but the rules for the M, for the mantissa, for the significant digits is going to be slightly different too. So the rules are different here in that to encode the mantissa, here we're not going to have a implied leading one. So this is slightly different. The rule here is we make it so that the leading digit is 0 and then immediately followed by the fraction. Okay, so this is just the slightly different rules for denormalized floating point numbers. Any questions up to this point? So then there were questions. Oh, there's a question here. Swapnil wants to work through an example. So that's a good idea. So let's work through a few more examples. The example that Swapnil wants to work through is let's convert the number 130 into a floating point representation. So we'll work through the same steps as we had for the normalized case, but this time we're gonna use a different input number. Okay, and instead of following exactly the example that Swapnil is gonna work through, right? So we have 130 is the proposed number, is the floating point number. And just to make it slightly different, let's make it a negative number. All right, so can we all agree on using this as an example? Just trying to think, let's, if there's anything I can do here to make it a more interesting example in this case. Yeah, I think this is fine. Actually, just to make it slightly different, let's actually make it a number like this. It's the same idea. And I think this corresponds to Yuchen's idea. Let's make it a 0.5. So let's make it a, let's convert this number, negative 0.013 to floating point encoding. This is our base 10 number. Okay, so anybody want to pitch in on what's the next step that we got to do here? So we say, first we got to calculate S. So sign in this case is negative. So S is actually now going to be 1 to make it a negative number. The binary representation of this. So we got to work through, we've taken care of the sign, and we've got to figure out what is the binary notation for this number. So 0.13, this equals So Xiaowei is suggesting that we have 0.0125, but this is actually not a power of 2, right? So we can work through, let's go through the thought process here. We can go back to our reference slide here. Right. So we can say, does this representation have a digit in the 0.625 digit? Bernice and Victor say no, too big, right? So we got to go to the next digit down. Next digit down is 3125. Is this smaller? Still too big. What's the next digit down now? Samuel says it's 15625. Still too big? What's the next digit down? So what is 1/2 to the power of 8th, right? So this has been 1/2 to the power of 7. So this is still too big. So we got to go down to 1/2 to the power of 8th. So Michael has that calculation here, which is 0.0390625. Okay, so we've actually cornered ourselves into this number. I don't think it actually divides evenly. So instead of doing this trial addition of the numbers, we'll just go ahead and calculate what is this in binary. So Xiaowei's got a conversion here. So this is this the exact conversion here? Likely not, right? Because we took some 130, we divided by a power of 10, and approximately the binary representation of this number is in this format here. So let's just run with that. And so what's the next step that we have to do? The next step is we are going to move the floating point. And so we have to figure out what is the floating point representation of this, where the mantissa starts with a leading 1 point something. And so this corresponds to this number. And we're going to move the floating point 1, 2, 3, 4, 5, 6, 7 digits. Okay, so Yu Chen and Victor both chime in. That's what we want to do. So we've taken our binary representation here, and we move the decimal point 7 places so that we have a mantissa that has a leading 1 in it. And to make it the same number, we are going to multiply by 2 to the power of -7. And so what we need to do now is we need to figure out what is the EXP field, what is the frac field. So to calculate the EXP field, we have to figure out what was the actual exponent, which we denote as E. So E plus the bias. So this is EXP. The EXP field is calculated from the E plus the bias, where E in our number now is a negative number. So our E here is -7 plus the bias for single precision floating point numbers is 127. And so in the EXP field, we will record 120. And again, so we need to record these as binary numbers. So 120 is in binary, that is 64 plus 32 plus 16 plus 8. So that's 120. And to represent this as a binary number, this is going to be 11111000. And this is the base 2 number. All right, so this is the 8-bit number that you would record in the EXP field. And what we need to do next is now that we've taken care of the EXP field, we also have to take care of the frac field. And to calculate the frac field, we look at the mantissa. Now, mantissa for this number is, we've gotten this binary string here. I'll make this a 0B just to emphasize this is a binary. This is also a binary. So mantissa is this value. And frac is just, we truncate away the implied 1 point. So the frac portion of this mantissa is 1010. So this is the number we record in the frac field for this floating point, single precision floating point number. So any questions here?
Excuse me?
Yes, please.
Is this the normalized example or denormalized example?
So this is a normalized example.
Okay, thank you.
Right. So while this may seem like it's a really small magnitude number, it's still well within the range of numbers that would be represented using normalized numbers.
What are the ranges for normalized and denormalized again?
So for floating single precision and double point precision floating point numbers, you'd have to have a exponent, a really big exponent, -126, a really large magnitude negative exponent for it to become a denormalized number. So for the example that we were working on there, it's still well within the range of normalized numbers.
Okay, thank you.
One question.
Yes, go ahead.
So in relation to our lectures, to the lectures on the 1s and 2s complement, would most modern systems normalize, like say, negative integers, negative floating point integers using 2's complement now, right?
Okay, so you're confusing two different topics here now, though. So in 2's complement does not play any role here. So 2's complement was entirely relating to integer numbers. And for floating point numbers, we do not use 2's complement or 1's complement for any of that. We just directly record what is the sign of the number, and we leave it at that. Thereon, after we recorded the sign, all of the frac field and also the exp field, all of that proceeds as if they were just unsigned numbers. So there's no such thing as 2's complement numbers involved here.
All right.
Okay, so kind of one final major point that we need to cover about floating point numbers is special cases. So I've been seeing in the chat box people asking, okay, so what about 0? How do we encode 0? So this comes to finally the last class of numbers, which is just the special cases. And this is where we store numbers like 0, infinity, and other kind of special error code numbers. So the way we encode 0 is just all of the numbers are 0. So exp is going to be 0, and the frac field is also going to be 0. And this actually leads to a case where in floating point numbers, we actually have both positive 0 and negative 0. But that's fine. That's just kind of a quirk that we have in the floating point representation. And then for different other combinations of the exp field and the frac field, you can use them to encode positive and negative infinity. And also another kind of number called not a number, which is kind of like an error code, which would pop up when you try to do illegal operations on numbers. So things like taking the square root of -1, or by trying to compute something like infinity minus infinity. This is neither 0 or any other number. If you try to calculate infinity minus infinity, then you get not a number. Right? And likewise, for trying to multiply infinity by 0, this is neither 0 nor infinity. This is not a defined number. And so in floating point numbers, you can encode whenever you try to do this kind of computation by raising an error saying that you've tried to calculate not a number. Okay. So Ember is asking what number or what bit is stored for S for each of these cases. So S for 0, right? It just corresponds to, so if it's 0 approaching from positive side, then S is 0, indicating that's a positive number. And if it's 0 approaching from negative side, quote unquote -0, then S equals 1. And likewise for infinity. So infinity, positive infinity, you distinguish between the two via the S bit, which encodes the sign. All right, so that covers the major topics of floating point numbers. We'll use next Tuesday's class to work through a couple more examples and also work through some of the more corner cases and properties of floating point numbers. But this covers the major topics of how to go from floating point numbers to real numbers and real numbers to floating points. All right, so any questions about any part of lecture today?
So when we get asked questions about floats on like an assessment, is it gonna ask us to like convert a number into a floating point, or like ask us about specific parts of the process? Like what kind of type of questions should we expect?
Sure, so for assignment number 3, programming assignment number 3. Programming assignment number 3 will have a portion where we convert from a bit string to a floating point number, and also vice versa. So going from floating point number and using a program to figure out what is the bit string for the floating point number representing that real number. Okay, so
what about questions on quizzes and stuff?
Can't guarantee what kind of questions we'll ask about that. So this will definitely be a part of the programming assignment. All right. So
thanks, Professor.
That's the major parts of working with floating point numbers. So now we've dealt with both integers and also floating points. So keep taking questions about any part of this or about program assignment 2. But otherwise, hope everyone have a good day. Yu Chen is asking, still confused about how in denormalized numbers, the EXP field is 0. So for denormalized numbers, it's just any number where the EXP field is set to 0. And for that, we just follow a different set of rules so that the number line around the number 0 is evenly spaced and covers the whole range smoothly. Xiaowei is asking, right, so sorry, back to Yu Chen's question, right? So it follows a different set of rules because there is no longer a implied 1 at the in the first digit. Xiaowei is asking, a lot of numbers can't be represented by this number. And that's true, right? So we do not have like all the precision and all the bits that we need to arbitrarily cover any portion of the real number line. The numbers that we do have access to are intervals, these points along the number line where there is a corresponding floating point number. And so there is a whole field of mathematics and computer science called numerical analysis, which talks about how to make sure that our computation is sound. Okay, so that, for things like solving differential equations, for solving linear algebra problems, in really extreme cases where you have really tiny numbers and also really big numbers, there's a whole study that's dedicated to making sure that using floating point numbers, you still get sensible calculations when dealing with those really big or small numbers. Okay, so if there's no more questions, I'll go ahead and end the recording and the session here. All right, take care.